Okay, so when it comes to aqueous solutions, there's really three different kinds of reactions: precipitation, acid-base, and redox. We're going to talk about precipitation, and then we'll talk about acid-base, and we're saving redox for later. So precipitation reactions mean a solid has formed. Okay, you're mixing together two aqueous solutions, meaning they are mostly water, but they've got enough ionic compounds in there that when they pour them together, they form a solid. So the solid that's formed is called a precipitate. For example, I did this demo in class. When I mix those two together in a double replacement reaction, the Pb and the K trade places, and you drop and swap charges. So you get KNO3 and Pb, which had a charge of 2, drops and swap with the I. That's your solid. So anything that remains aqueous, which is what the KNO3 is, that's an N, I don't know what happened to it there, is still part of the solution. It hasn't gone anywhere. It's still there. It's just floating around. It didn't turn into a solid. It kind of sits around and watch. Unless you get a solid, then the reaction didn't happen. Nothing happened. All you did was mix together two different things and nothing happened. It's not like it reacted and changed in any way. So you have to have a solid form. So solubility rules, which you will need to memorize. Anything that ends in NO3 or acetate is always aqueous. Anything that begins with an alkali metal, that means column 1, or ammonium, is also aqueous. So those are our always rules. And the way I remember them, 3 A's and an N. Ammonium, alkali, acetate, nitrate. Okay, again, alkalis are column 1. Now after that, they're not always aqueous, but they're usually aqueous. So these are the usually rules. Halides are column 17. And they are usually aqueous unless they're mixed with silver, lead, or mercury. And you're not going to see mercury very often. Sulfates are usually aqueous, except for silver, lead, and mercury again. And then these guys are the heavy alkaline earth metals, the ones towards the bottom. Okay, so these are my usually rules. Okay, on the next page, this is the rules about solids. These guys are almost always solid. So most hydroxides are insoluble unless they fall under my first rule, the 3 A's in the end. So if they begin with an alkali or they begin with ammonium, they are aqueous. But other than that, they're solids. Okay? And then the last rule is kind of like our everything else rule. That's what I refer to it as. Okay? Everything else, if it isn't followed by the first 4 rules, or number 5, I guess, is a solid. Okay, so this is my rules for solids. So hydroxides and pretty much everything else that isn't mentioned in the first 4. Okay, first 4 rules. So in a precipitation reaction, you're going to use double replacement. It's pretty simple. What happens is the anion and cation trade places, trade partners, and a reaction only takes place if a solid is formed. So for the first one, the Ag and the K are going to trade partners. That means you're going to drop and swap. So the K goes where the Ag was, and the Ag goes where the K was. So I'm going to have K, 1 plus, with NO3, 1 minus. Drop and swap those and get KNO3. Then for the Ag, it is also plus 1, and Cl is also minus 1. Oops, minus 1. So I would drop and swap those and get AgCl. Balancing it, it's balanced. I have to identify the solids. So I'm going to look at my rules for solubility rules, and I'm going to remember 3 A's and an N. Nitrate, automatically aqueous. So Ag doesn't fall under either one of those rules, and neither does Cl. However, Cl falls under the third rule about halides, And most halides are aqueous except for those mixed with silver and lead and mercury. Once I have a solid, that means that reaction actually happens. Okay, if I was to do this one, the Zn and the Ba trade places. I'm going to have the Ba, which is positive 2, with sulfate. And I have memorized sulfate as negative 2, so drop and swap and it goes away. And then the Zn on the periodic table is one of the ones that's always 2. And nitrate is negative 1, so when I drop and swap, I get that. So then I have to look for a solid. All nitrates are aqueous. However, if I look at the rules for sulfates, it says most sulfates are soluble. Exceptions are the silver, lead, and mercury, as well as the heavy alkaline earth metals. So this is my solid. And balance this, it's balanced. Okay, last one. CD and Na are going to trade places. I'm going to have the Na 1 plus with Cl 1 minus, and CD, which has a charge of positive 2, with nitrate, which is negative 1, so CdNO3. And then I have to balance it. Let's put a 2 here and a 2 here. And I have to identify a solid. All nitrates are aqueous. So that one's out. And then all alkalis are also aqueous. That means this one is no reaction. Now, I will tell you that I know and you know that NaCl is salt. And you know that salt on your French fries is a solid. However, when it's in something that's aqueous, it is aqueous. There's always somebody every year who tells me that sodium chloride is the solid that forms. It is not a solid if it is in water. Salt dissolves in water. Okay, so there's 3 ways of writing them. Molecular equations, which is what we just did. Drop and swap everything. So if I was to do this one, the Ba and the K trade partners, I'm going to get KNO3, drop and swap 1s, and BaCO3, drop and swap the 2s. This is my solid, this is my aqueous, and there are 2 of those. Okay, that's a molecular equation. That's what we've been doing all along. However, if we were to write what's called a complete ionic equation, what that does is it shows everything that is aqueous as ions and the solid precipitate by itself. So if I was to do that one, let me rewrite it. Anything that's aqueous, I'm undropping and swapping. I have 2 Ks plus a carbonate plus a barium plus 2 nitrates. Anything that's aqueous, I undrop and swap. Over here, I have aqueous. I have 2 Ks and 2 NO3s. And this is a solid. The solid you don't do anything to. You leave it exactly as you found it. That's your solid. Then, spectator ions, when you take them out, you get what's called the net ionic equation. What it does is it shows change only. Okay, so the only thing that changed is the phase or the state of matter for the barium and the carbonate. The K plus is exactly the same on both sides. The nitrate is exactly the same on both sides. They didn't do anything. They sat around and watched. The only thing that happened is you had carbonate go from aqueous and barium go from aqueous to form a solid. And that's a not ionic equation. So when it comes to doing stoichiometry with these reactions, the biggest thing you need to remember is that you want moles. You always want moles. So if you know the volume of the solution and the molarity, all you have to do to determine the number of moles is multiply. So liters times molarity will give you moles. And I will say it over and over again. Liters times molarity will give you moles, and this is what you need to do any kind of stoichiometry. So, sample problem. I give you a balanced equation, and I tell you what mass of solid, so we're looking for this stuff, that means grams, is mixed with excess. You guys remember the little trick about excess? Cross it off. So all you're going to do is take the liters, 0.1 liters, multiply by the molarity, do the mole ratio, 1 barium chloride to 1 barium hydroxide, and then you change from 1 mole into grams, which is 171.3. So it is very similar to our other forms of stoichiometry. The only thing that's different is we find the moles here by doing liters times molarity. After that, this is the stoichiometry, and that's just a conversion. You get 7.28 grams. Okay. Next one. So this time you have to figure out what the products are. So the AG and the MG are going to trade partners. You're going to get MgNO3, drop and swap the 2, aqueous, and AgCl, solid. Okay, and to balance it, you put a 2 and a 2. So what mass of precipitate is formed when excess? Ignore 75 milliliters of molarity. So 0.075 liters, 1 liter, 0.05 moles. It's 2 AgNO3 to 2 AgCl. 1 mole is grams, 143.4. Multiply it out, 0.54 grams. A couple of things I want to point out. Make sure you divide by 1,000 to get liters, and then liters times molarity will give you moles, and you can just go straight into stoichiometry from there. Okay, now I'm going to add this one in because this is often what you see with stoichiometry problems. They give you little pictures and they expect you to relate the numbers they give you on a large scale to what's happening at the molecular level. It's called particulate understanding. So in this experiment, they take 1 liter of a 3 molarity solution of this mixed with 2 liters of a 4 molarity solution of Ki. Illustrate the initial conditions below and use one picture. I'm not going to use one picture. I'm just going to tell you how many there are to equal 1 mole of the ion. So to find moles, liters times molarity gives me moles. So if I do 1 liter times 3 molarity, that tells me I have 3 moles of this stuff. And if I do 2 liters times 4 molarity, I have 8 moles of Ki. But when you put them in water, let's remember our dissociation reactions. This breaks apart into Pb2 plus and 2 nitrates. This one, when you break it apart in water, it turns into K plus and an I minus. And for every 1 mole of PbNO3, I get 1 mole of Pb, but I get 2 moles of NO3. So if I had 3 moles of this, I'm going to get 3 moles of Pb and 6 moles. So I have 3 Pb2 pluses and 6 NO3s to start. Similarly, this one, it breaks apart in a 1-to-1 ratio. So if I have 8 moles of Ki, I'm going to get 8 moles of K and 8 moles of I. So I have 8 K pluses and 8 I minuses. And this is what happens before I mix them together and they react. So write the balanced molecular equation. It's PbNO3 2 plus Ki. Double replacement, the K and the Pb trade partners. So I'm going to get KNO3. When I drop and swap charges 1 and 1, this is aqueous. And I get Pb. Pb has a charge of 2. I drop and swap. I get PbI2, which is a solid. Balance it like this. So it says determine which solid would precipitate. That's PbI2. Okay, so at the bottom down here, we have solid PbI2. The relative volume of the mixture, assume the solid occupies negligible volume. Well, if I had 1 liter here and 2 liters here, this will be 3 liters. And then how many moles of each ion are in solution, and illustrate in the product beaker. So first thing I want to talk about is those spectators. Okay. Spectator ions do not do anything. They do not change in any way. That means my Ks, I still have 8 K pluses floating around. My NO3s, I still have 6 NO3s floating around. Notice, I didn't look at the product part of it. I looked at what they started as based on this information here. Okay? They don't react. That means I don't include them as part of the reaction when it comes to figuring out how much I have. I don't have to do stoichiometry on them because they don't react. So the amounts that I start with is the amounts that I end up with. That means liters times molarity will give me moles for those guys, which is what I did initially. However, some of the PB and some of the I turned into my solids, so I have to determine the limiting reactant. So if I have 3 moles of PB I2, not I2, PbNO3, that's my reactant. It takes 1 PbNO3 to make 1 PbI2. It could make 3 moles of the solid. But it's a limiting reactant problem because I have moles for my other one. I had 8 moles of Ki, and it takes 2 Ki's to make 1 of my solids. That means it could make 4 moles of PbI2 solid. Well, clearly what that means is this is the amount I'm going to make, and my limiting reactant is right here. Okay, I'm going to have to go on to the next slide, but kind of keep in mind these numbers. So what I started with was 3 PBs, 6 NO3s. I had 8 Ks and 8 Is to start with. Then I mixed them together. They went to 3 liters. I still had the 8 Ks floating around. I still had the 6 NO3s floating around. Down at the bottom, I had solid PbI2, and I had 3 moles of it based on my previous limiting reactant problem. So my limiting reactant was the PB. That means this guy is excess. Okay, so it says determine the concentration of all ions remaining in solution and the theoretical mass of solid formed. Well, Pb2 plus is my limiting reactant. There's none of it. It's gone. 0 molarity. The NO3 minus didn't really change in terms of its moles. I have 6 moles in 3 liters. It's 2 molarity. The K plus is very similar. I had 8 moles in 3 liters. It's 2.7 molarity. To find the grams of my solid, I just take 3 moles of PbI2, 461 grams, 1383 grams of solid. So those are all the easy things, the really obvious things. What I have to figure out is how much I minus I have left. I know it's still in 3 liters, but I need to figure out how many moles I have left, and it's my excess reactant. If you remember, the rules for excess reactants is you must subtract at some point. It doesn't matter how you do that as long as you're consistent. So what I had, previous slide, was I had 4 moles of PbI2 from this stuff. I'm going to subtract my 3 moles of PbI2, and that gives me 1 mole of extra PbI2 from the I minus, and 1 PbI2. Once you have it in moles, it's pretty simple. 1 mole of PbI2 gives me 2 iodines. That means I have 2 moles of I minus left, 0.7 molarity. Okay, it's not that hard. You kind of have to pay attention to what you're doing. Oh, no, yeah, 0.7 molarity. Yeah, that's right. Just be real consistent with what you're doing. So when the numbers are not so nice, it's a little bit harder. So for this one, I'm going to do the stoichiometry to find the limiting reactant. 0.025 liters, 1 liter, 0.67 moles, 1 H2SO4, 1 CaSO4. And I'm going to stop at the moles. 0.035 liters, 1 liter, 0.40 moles, and it's 1 calcium chloride to 1 calcium sulfate. So if I stop right there, find the moles of CaSO4, I can find out which one's my limiting reactant. So I have 0.0168 moles and 0.014 moles. So clearly my limiting reactant is the calcium chloride, and this is how much it produces. So I'm going to change that into grams, which is 1.91 grams. That's my answer to the first question. What are the concentrations of the ions remaining in solution? Liters times molarity gives you moles. The total volume is 25 and 35, 0.060 liters. So for the molarity, Ca2 plus, it is 0 because it's my limiting reactant. And that's easy. The molarity of the chloride is going to be those moles, right? 0.035 liters times molarity gives me the moles. Then, so 0.014 moles of chloride, calcium chloride. And then I need to multiply by 2 chlorides for one of them. So that gives me 0.028 moles over 0.06 liters. So the molarity of that is 0.47 molarity. That's one of them. The molarity for the H plus, similar. It's a spectator. It's liter times molarity. Gives you moles. So it's going to be that number, 0.0168 moles of H2SO4. And inside there is 2 H pluses, which means the moles are, I'm going to round it up, 0.034 moles over the liters, which is 0.57 molarity. Okay, now I've run out of room, and so I'm going to erase what I have, and I'm going to figure out the excess ion, because I have 4 of my ions. The limiting reactant, which is always 0. My spectator ions, the hardest one to figure out is always the excess ion. So I'm going to erase a good chunk of this. I hope. It does not want to erase very well. Oh, there we go. All right, so I'm going to do the excess ion. My excess ion is the sulfate. So the molarity of the sulfate, anytime you're going to find excess, you have to subtract somewhere. And I'm going to take these two numbers and subtract. If I do 0.0168 moles of CaSO4, and I subtract 0.014 moles of CaSO4, what I have subtracted is the moles of CaSO4. And so what I need to do is change that from calcium sulfate into sulfate. And divide that by the liters. And that gives me the molarity of my excess ion. Okay, but you have to be real careful about what you're doing. I subtracted the moles. That gave me the moles of one of them. I need to turn it into the moles of what I'm looking for. Happens to be a 1-to-1 ratio. It might not have been. The chloride was a 2-to-1 ratio. The hydrogen that I did before was a 2-to-1 ratio. So you have to pay really close attention to what you're doing.